log error is the number of samples, that is the error, right? If I plot error against log n, what do you expect? You will get a straight line. Oops. So maybe that's not a straight line. Anyway, that's a straight line for now, right? So you will get this behavior. So instead of looking at the error, if you look at squared error, it's a bit easier. You get this, right? It's just the square. And in this case, this slope is -1, right? If it's squared error, then your slope is -1. That's how your error behaves. And obviously, remember, this is a log-log scale. So it may be a bit misleading to say, oh, this is really nice because if I'm here, the error drops a lot. But if you're here, you've gone pretty far on the n-axis. To get log n to this, you have to go really a large number of samples. So that is the problem with Monte Carlo. Of course, we have done one step better than previously, but this is our problem. Okay, so the interesting thing is this is called convergence rate of estimator mu n. These are just terminology, but you understand the idea is now that the slope falls off like this. Convergence rate tells you this could be with respect to error or squared error. It's just a factor, right? Let's say for squared error, we say -1, which is nice and easy. So the convergence rate is just that, right? -1. Why is this relevant? This is relevant because once I have many strategies, I may see that this is estimator A, estimator B. I'm plotting log error or squared error, whichever one you want. C, E, and so on. Right? We have different estimators. Now, this is just for reference in case you look at it later and you're wondering what it is. Right? Now, this is the most common question in any application domain, which is, oh, I have seen there are 4 different ways to estimate my integral. Please tell me which is the best. That's not a question anyone can answer, even if you know. So remember, to get these curves, you need to do a lot of analysis. To prove that the Monte Carlo error is 1 square root of n, took a lot of analysis, right? And for each of these estimators, let's say you spend months and months with all the maths. Finally, you say, okay, here's the error profile. And somehow you came up with the error profile. And we'll look at examples. So for example, quasi-Monte Carlo, if C is Monte Carlo, A could be quasi-Monte Carlo, which is another way to estimate, and that has a better slope convergence. So error falls off quickly. So you need fewer n, right, to get the same error. But we still can't answer which is the best estimator. Why is that? Because depending on whether you choose n here or here, right? So if I choose n here, right, and I rank these algorithms, right, at some point x, which is the best? D is the best, and B is the worst, right? Whereas if I choose at this point y, B is the best, right? And what is the worst? C is the worst. Yeah, so you got the hang. So basically, this means that in your application, unless you know what your sampling budget is, so for example, you want to do this in real time, or if you're in a medical application, you don't care, you'll throw it to a supercomputer, wait for a month, but I want the correct answer. then you may want to prefer something that for larger n gives you better error. Right? So if you prefer a supercomputer, do you prefer X or Y? So let's say we'll give you two examples. Okay, I don't want to use A again because there's A. So let's give two situations, right? So this guy here wants quick feedback. Let's say it is an interactive thing that immediately. Let's say the doctor is looking at your scan, and in a millisecond they want to know something, recommendation, expected. Let's call this expected prognosis, right? And the doctor wants to know immediately, right? And let's say on the other side, the doctor then says, okay, I'll see you in a week. We'll analyze your results and tell you. And then they have this massive supercomputer they can throw it into, right? Now, for each of these situations, would you choose, which algorithm would you choose? So let's take the real-time one. The doctor wants it right away. Which algorithm, which estimator would you choose? Huh? D. Because you're going to only afford a few samples, and you want the best estimate you can get with these few samples, right? So this, for example, D, right, is good for real-time applications, right? Whereas if you have plenty of time, where would you be? Which estimator would you prefer? I have a supercomputer. Which one would I prefer? C? Why C? B, right? Because even here, there's some error, whereas B is now going to be almost zero. Right? I've exaggerated the drawing. Obviously, you will not get such a big difference, right? But this is the best of the lot, given high computational budget. Right? Is that clear? Yeah, if you want to take notes, you can take notes. I'm going to share this, but usually when you write, you tend to remember, right? So, yeah, so as you can see, that's quite nice, right? And this is all exaggerated. So, I mean, you will rarely get something like this. So it's exaggerated for illustration. I'll write that there. Right? Okay, so now that's pretty clear, right? So when you see sampling algorithms, you can simply plot if you know their profiles, and then make a decision depending on your application. In fact, in computer graphics, when these guys design these animations and then look at them, they have what is called a previs. Previs in the animation industry. So let's say the director for Bahubali goes to CG company and says, oh, how far have you done? How far have you finished this project? They cannot show them the final clip, right? It's going to take months of rendering on huge 30,000 core farms. So what they do is they say, okay, this is roughly what it's going to look like, and they show previs. For the previs, a lot of people use different algorithms. Obviously, they will use D for previs because they can quickly show every day's work to the director, and they'll come and say, oh, okay, that's useful because the director may say, oh, this looks completely not like what I want. So let's change the angle, let's change this, and do all this stuff, right? So it's very useful. And then when the final thing comes, the director will say, okay, bake this. When they say bake this, this means, okay, send it off to the rendering thing. We have settled on everything. Then what they do is they will run all the costly algorithms. Well, obviously, you can see a problem here, right? They may expect to see the results that D gives, and they may end up seeing B. So the director will come back in, and this has happened many times in the past. So come back and say, wait, your previous was showing this. What's happening here? That everything's different, right? And then they have to explain, no, sir, we used a different algorithm there. The director doesn't care, right? Like in the end, your previous should look something like. So there again, there's a problem. There's a problem in if you want to use the same application, there should be some coherence between D and B, right? And this introduces a lot of problems. So there's a lot of active work on this in computer graphics. So even though I think people have pretty much figured how to do this in computer graphics, this is still very widely open. So current research in rendering, a lot of it is focused on that. How can we get a very good estimate early on and not have it linger for so long and have some resemblance to the actual ground? And what do I mean by resemblance? It's this thing here, right? So formally what it means is this thing that we wrote here. Oh, sorry, not this. This thing that we wrote here, saying the expected value of mu n is I, is telling you that even if you run it for infinite samples, this is how it's going to behave. So that's an important thing. Because without that, it really doesn't make sense to look at this, right? If at infinite samples you will not get zero error, then your curve is going to, at the end, sort of asymptotically reach this. It's never going to actually get to zero. So these are all things you tend to prove about the sampling patterns. Okay. So that is to give you some idea about why we study error, why we study convergence rate, how can we make deductions from convergence rates and so on. Any questions? Everything clear? Okay. So that is, so now let's maybe take a small so we came up with this ad hoc way, right? This Monte Carlo thing. And it was not very different initially. This was many hundreds of years ago again, that this French guy is quite rich. He could afford to spend his time dropping needles. And he said, I want to estimate the value of pi, right? He said, what is the value of pi? He said, it should be easy, right? Just like we came up with. If you draw a circle in theory, and you drop, so you draw a big circle on a sheet of paper, put it in this square, right? There's a square tile, and I drop stuff that sticks without bouncing and so on. If it lands in here, and I count the number of things that land here, the number of things that land here, and I take the areas into account, I should easily be able to deduce the value of pi, because I know the area here, A1, I know the area here, A2, and I know the total number of samples, things that I dropped is n, right? So if the number of dots inside this big square, let it be n. Let's call it n1. And then this is n2, n equals n1 plus n2, right? Then you can take, you know the ratio A1 over A2, so you know how many proportional to the area of the circle, you know how many you expect here, right? So you expect that n1 divided by a1 should be equal to n2 divided by a2, right? That is what you'd expect. So if you know this length of the side S, and if you know the radius, these are all easily measurable on your drawing, then you should be able to easily write n1 divided by s squared equals a2 s squared minus, let's say, pi r squared equals a2 divided by pi r squared, right? And then now you can solve. The only thing you don't know is pi. You can measure n1, you can measure n2, and you do this. If you have enough time like he did, you drop it. You can sort of say, you know, iteration. So I used n1, n2, iteration number 1, 2, 3. So there's some good YouTube videos on this. I won't dwell on this for long. But, oh yeah, sorry. This is n2. Yeah. Then you can imagine what he did, right? Meticulously, you go through this. You count how many fell in, how many fell out, tabulate it, iteration 1, do the same thing, iteration 2. You repeat this experiment just like we've done in many of our labs, and you come up with some estimate of pi. So you will get some estimate of pi, and that was the breakthrough. So he didn't quite do this experiment, it was slightly different. Instead, he dropped a needle, and he looked at the orientation of the needle with respect to some parallel lines. But in principle, that's the idea, right? And you get estimates of pi. Now remember that every estimate of pi, right, is a random variable in the sense that these things happen randomly, and we are assuming that the drop was a bit random, which need not necessarily have been true, because sometimes you may have moved here and there. It's not controlled to that extent. He might have tried to make sure, like, have a string or something. Anyway, so you can kind of do tricks to do this. Anyway, so at the end, what the conclusion was, and this was sort of transformative for mathematicians as well at the time. They were like, oh, wow, this is beautiful. We can just estimate things we had no idea about by using a random process. So that was the birth of the whole Monte Carlo thing, right? Like, it's completely random process, and there's structure coming out of it. We can estimate things like that. Then it was much later, during World War II, when they were developing the atom bomb in the US. People wanted to study how neutrons, this is very relevant to computer science, graphics, because a lot of methods were born from this. People wanted to study how neutrons bounce against each other and fly around. So this is called neutron transport. It is, if you have a room or whatever space filled with neutrons, they move. And people wanted to estimate the density of neutrons or the probability of two neutrons colliding and things like that. And this was very, very complicated, because you could write down some physics, but you had to simulate them to actually know whether they would collide or not. And it was at a scale where they could not actually run experiments measuring how many neutrons collided. So they were in deep trouble, because they needed to compute things which at the time, with their compute power, was almost impossible, right? Think back 1942, they're still working with punched cards, and they were excited that the computer was there, but it was not good enough. So then they said, oh, look, let's look at this stuff again. And there was this one person who said, okay, let's see if we can apply these random processes, right? And then three of them, basically Ullmann and Metropolis and von Neumann, the three of them discussed, and they were like, oh, let's come up with this stuff. And they proved a lot of things. They showed that you can estimate integrals or expectations by using random processes. And that was a revelation. Suddenly now it meant we can simulate using random processes and then measure things in the simulation and make conclusions about distributions. That was the birth of Monte Carlo. So this is not very far away from what we have described there, right? Like, so we had, sorry, what's your name? Pravesh Alam. So Pravesh Alam said, okay, we can throw random numbers, and yes, but the hard work was done by these guys proving a lot of this stuff. Any questions? So now I will go to what I actually intended to do, which is, I'll start off with some general idea of the main part of the course. So this is a course, as I said, that we gave at SIGGRAPH. It was the three of us. So Gurpreet and Wojtek were at Dartmouth College at the time. Gurpreet has moved on to Germany now, and I moved from Heriot Watt to University of Edinburgh. So I kept the old slides because I also wanted to give them credit as well, because we developed this, many of these things together. So we have done all of this. So let's take a little break now. I'll show you a concrete example for all the stuff that we've discussed. So this was a paper we had in 2014 where, this is an image that was generated purely virtually. Right? There was no such thing, obviously. There's no flying vehicle. I can't say that for many more years, but now I can say it's quite obvious. We had the 3D model for this, and this whole background, all that you see, was a real photograph. Right? So just like in the movie, somebody went to the top of some building in Los Angeles. They took a camera and they kind of got a panorama, 360 panorama, and they put the image on the internet and said, here's an environment map. That's what we call it. So it maps the environment And then we said, okay, now let's assume we have a vehicle in this environment. It's a classical thing that computer graphics people do, and say, okay, now tell me for this model, how much light do we expect to see at each of these pixels? Right? That's the question that we want. So this is very similar to when you take a photograph. So again, I'll draw parallels because otherwise you may think, oh, what's the big deal, right? So if you take a photograph and each pixel in that is a CCD element, it receives photons and spits out electrons as voltage current, right, or whatever charge. So it receives some number of photons, integrates them, if photons from everywhere, and then spits out this charge. Okay, so this, what we're asking is at each of these, if there was a camera placed here, and if there was a car here with this shape in this environment that I've taken, at each pixel of this virtual camera, which is called a virtual pixel, what would be the recorded charge by this camera? Obviously, there is no camera. There are no photons actually coming. So we have to simulate the whole thing, right? And this may be similar to problems you would have seen, right? So if you know, for example, that there's a distribution on the number of cars leaving Bangalore, right, going to Mysore, then the question may be, you can phrase this as, if I'm standing at the Mysore Road junction, how many cars will I expect to see passing me at any given time, right? And you may not actually have the measurement, but you can estimate this. And that's what we did here. At each pixel, we estimated how many photons will be received, and therefore what charge will go. And what I'm going to show you now is we used Monte Carlo for this. We used these few pixels here, right, to illustrate this. And actually, what we drew there was a bit exaggerated, but was not very different, right? So I'm not going to tell you what these methods are. They're irrelevant for the current discussion. What is relevant is these are 4 methods that have been developed over decades, okay, by clever people who've spent a lot of time thinking about the problem. So we took 4 competitive methods, and we said, let's look at this, okay? And our computer graphics people, what they do is they will look at this and say, oh, I'm going to use method 1 or method 2. And people fight over this at conferences, saying method 1 is better than method 2. Or no, method 3 is the best. And people will show you proofs, they will show you images, they will show you all sorts of things. But what we wanted to do was to see, look at it in this space that we've discussed before and see, is A really better than B, right? And so we took, can you read these letters at the back? Yeah. So we took each of these, and these are A, B, C are the pixels that are labeled there, okay? And we plotted for each of the method different colors, these bars. And straight away it's obvious that depending on the pixel, certain strategies are better than others. Not only that, even within a pixel, different strategies have different slopes and convergence rates. So it is not at all obvious. Even these, so this, we just hand selected a few pixels, right? There's no clever way to choose them. So we just said, oh, let's look at it here and let's look at it there. And we find that, like I said, right, if you draw these lines here corresponding to, this is the point where these intersect is 141 samples per pixel, whatever that number means. Which means if you're using more than 141 as n, then the white curve becomes better. If you're using less, then the other curves, other curves are better. But that is not necessarily the case here. In fact, it actually is, there's one more somewhere, yeah, here. It's the flip. If you use large number of samples, white becomes bad. It's higher error. If you use fewer samples, white becomes bad. So then we realized that actually there's a huge problem here. People who have been thinking about this stuff and fighting over which algorithm is better have not looked at it in terms of, look, things are different at every pixel. And that is one of the problems of analysis. I've been so far saying, oh, analysis is great, right? So one of the problems of analysis, especially theoretical analysis, is a lot of this does not consider the actual data. When we actually put this particular shape in this particular environment, suddenly the data has a certain distribution. And it may not be easy to characterize that distribution, but the fact that there exists one means that we cannot simply go with whatever analysis we have. Mind you, all the analysis is still true in that if they said something will converge at square root n, it converges at square root n, right? So the thing that maybe was not obvious when I drew this earlier, because I didn't want to draw too many things, is in this curve, I can have another algorithm just like D, right? That is here. And this has exactly the same convergence rate as D. So the slope will tell you the same thing, but it's so far above that its error will be much higher. Right? So it's not enough just to look at convergence. You also actually need to look at what the error is. And you can see that comes into play here, right? Some algorithms, they may have a better slope and be lower, but some may have the same slope, but they may be better. We found that this just became too hard to write down. But something is important here, right? Somehow we need to characterize this. So we need to look at a combination of convergence rate as well as absolute error. And I think the reason that this paper got published was because people realized, even though, so we proposed some analysis in it, but it was clear that our analysis was not in any way the final word on this. What people liked was the fact that we exposed this problem, right? Suddenly then, this means there's no point fighting over which algorithm is better and so on. Even for a same model, same data, different pixels have different behavior. So it's just hopeless to say that A is better than B. And so so this is what makes it such a complex thing, right? Is that we're nowhere close to knowing all this stuff, right? So if you have a complicated application where you have data coming in from different, maybe on one particular example data set, that even one data point that you looked at, I consider this one data point, right? Because there's one environment map, one 3D scene, and one view. Such a restricted data point shows so much variation, right? And so you may see that you tested on something and you cannot come up with a conclusion that this is better, right? So just bear that in mind. So that's why there's a lot of room, I think, for research in this. Yeah, so this is all the stuff that I've shown, right? Yeah, so this is different. We can skip this. Yeah. So let me give you a brief idea of why integration. So it may not be obvious. I just showed you this car and all these fancy images. Why is this mathematically relevant, right? If you look at a picture that we take, people have known for centuries, right? I can almost say millennia, that I can say millennia, that if you take a picture, if you have some scene there, and that is your sensor, that this will project into a certain thing. You can get what is called the pinhole camera. The painters used to use that. So they would put a screen here, and then look at the amount of light at each point and choose their paint and paint over it till it matches. And they would get these amazingly realistic pictures, which are in some sense just photographs, right? That has been known for millennia now. But this point, right, where they decided what color to use there, that is what makes it realistic. If we just drew a black dot or whatever, if we just drew that, we would get an outline, some shape. But if you want to know that, then you need to account for what is called radiometry. Radiometry is the amount of light, how many photons arrived at each of these. In those cases, that relied on a skilled expert who would decide, okay, that requires this color from my paint, still not quantified, right? Then centuries later, people like Da Vinci and people who, if you've been to any of these places with really beautiful murals inside, in Italy, they have some of these fantastic frescoes in the churches and cathedrals. They had a better intuition. They had modeled light in their mind, but still not formally. But this is very important, this radiometrically accurate simulation. And that is what we use computers for. So when I said Frozen used whatever computation, it used it to estimate how many photons would come there. Yeah, so for computer games and things, this may be enough. So if you use OpenGL or other game software, perhaps you can get the projection and then add some texture and fake it to look like it's pretty real. The advantage with that is it's super fast. We can do this very well because our graphics cards like NVIDIA and so on, they've evolved to do this. That is their sole purpose. And now people are saying, oh, we want to do more with them. And we're still in early stages. So this was a key paper, ray tracing, which showed how to do this projection. So yeah, so radiometric fidelity improves how realistic it is, right? So for example, this one is manually painted, right? And this is an art movement called hyperrealism, where artists wanted to create realistic images, and they looked at things and they're able to paint virtually indistinguishable images. And our goal is now, we don't want to spend hours, right? Obviously the artist took many, many hours for this. And we want to do this fairly efficiently. So that's the high level goal. So any questions before that? No. So actually this may be useful to show. So I'll quickly go here. I think, yeah, let's do this and then have lunch maybe. So this is the course that I teach, that I taught last year. This year I'm not teaching it, but maybe next year again I will, on computer graphics. And I can show you the introduction set of slides. Yeah, I'm just kind of trying to show you. So I started that one so I start all my exams with a test, right? And in this case, I showed a bunch of images to students who were taking this computer graphics course. And this we can just do for this course. It's more just as a way to test if you're calibrated, right? So I'll show you a series of images, and in your mind, try to guess whether it is a real photograph, it is computer graphics generated, or it has been somehow created by an artist. Okay, and then in the end, I'll tell you. So that's the first image. Second image. So as you can see, it's quite hard, right? And what people have done is they've shown these things to many, many people like you to get an idea of what cues people look for, right? So the people who do research on this, they look at, do people look at, the graininess, the natural appearance of the angle, camera angle, various things, and you would have thought about it yourself as to how to decide each. So any clues on whether that was real or fake? Fake? Okay, that one's real. This one's fake. Okay, that's real. Yeah, that's real. This one's real. That one's fake. The previous car is fake. This one's fake. So the two fence images are very similar, right? And so people played on this idea that, look, it looks a bit crooked. People are like, yeah, someone probably held the camera crooked. And these are things that they exploit. This one's fake. That one's fake. This one was painted. So actually, I shouldn't have shown you that image because very similar, right? This plastic sheet. So this one is an oil on canvas. This one's fake. This was real. This one's real. This one's real. So the black one was fake. So I took similar images. This one is real, fake, sorry. This one's rendered, yeah. This is real, right? So, I mean, it's very, very hard. This, any guesses? Painted? It is actually a sculpture. So there's 3D sculpture. So this one is rendered, it's fake. This is real. This one's rendered, probably easy to spot. This one is real, because the previous one was fake, right? Yeah, this one. This is real. This is pencil, sketch. And this one's real. So as you can see, it's fairly advanced, right? I mean, it is not straightforward to look at these images today, which means the simulations are also very accurate to perceptual levels. As I said, quantitatively, it may not be. Of course, not only do we want to simulate light and geometry and all this stuff, if we look at pictures we take with regular cameras today, they have so many different variables, right? We may use lenses. So if you're a photographer, you may straight away spot that that is not a natural lens. Or you may spot, look, there's a bit of focus with the fence images, or you may look at motion blur cues. And so when we simulate, all of these is important. Materials, for example, right? Like the image of the flying car that I showed you was so fake. Even if it was a real car, you would have looked at it and said, look, that material doesn't look real, right? Whereas some of the rendered images here, they had realistic material. So how do you model material? So all of these things are modeled in computer graphics. And then in the end, you ask, if I throw light on this whole big model, how many photons is going to come off? Right? That's where the simulation bit comes. So what we call this simulation is it's a bit like what I explained in neutron transport, except instead of neutron, it's photon. Right? So it's still a transport process. The transport process involves some source, some particles, and some sensor. Right? And what we're doing here is simulating this transport process. I use the word transport here because this is really what we call it. It may be very different from the transport that people obviously are studying here. But in some sense, there is this transport mechanism, right? Things go through, especially if you have objects like wax or even bottles filled with some colored liquids or something. Then the photon goes in, it kind of bounces around inside this bottle, right? And then comes out of somewhere. So there's a whole transport process happening inside. And we measure what is called radiance, to be precise. I guess kept calling it light and intensity and so on. This is watts, that's the energy of power, divided by unit area, steradian, which is angle. So it's telling you how much energy is traveling in a certain direction at a certain point. So for example, this notebook, if you're in space with a satellite image, may look almost like just a point. And that point has some light coming in a certain direction, steradian, per unit area. That is what this radiance is. And you can think in your own application, this could be sound per unit area per steradian, like in the microphone example. Could be the number of cars coming in a certain direction at a point, right? You could frame this as any quantity in your area, in your field. But the idea is we want to know these photons that are emitted from here. We would like to know how many of them survive after all these bounces and how many of them make it to these pixels on the screen. Now, if you think about it from a Monte Carlo perspective, what are you doing? You're going to take millions of xi, what we call, start from here, and then have some simulation. So they arrive at this material, and that material may say, oh, when you bounce here, you're going to go in this direction. So it throws you off in some random direction. Then you follow it through the scene, keep bouncing. So these are all models. You have meshes, right? 3D meshes like the car, and you have some material specifications and so on. And then you see which of these actually went in here. As you can imagine, if you throw billions of samples from here, barely a handful will make it into this. Right? They may bounce off everywhere else except here. And if your CCD is a 35 mm sensor like this, somewhere in the corner of that, let's say we modeled this entire room, and we have all these things emitting photons, and we put a camera at the top, or let's consider the camera here, right? and we want to know how many go into that sensor, you can imagine they will bounce all over the place. Many of the stuff will exit, a few of them will make it through. So if you launch 1 billion photons, you will get a few photons here. And using that, you want to estimate what the image will look like. So that's the computational problem. And just to make things formal, we'll resume this after lunch. But just to make things a bit more formal, this is what it looks like, right? So at every bounce, like this notebook that I showed, at every bounce, this is this rectangle at the bottom, centered somewhere. We have light arriving, radiance, which I called, arriving from different directions, right? Li, just like xi, this time we have Li coming from different directions. And let's say we want to know in the direction Lo, what is the radiance, right? So the radiance, outgoing radiance, Lo, is some integral over this domain. So hemisphere here, you integrate over the hemispherical domain, the incident radiance. And what is this? This is some rho which tells you what is the reflectivity of this material. This material might tend to reflect photons more in that direction. Then this rho will be peaked in that direction, right? So it's some probability distribution. And you may have some measure, let's leave that out for now. That's the integral you would like to estimate at every bounce, right? This is just one bounce. If all of these things are emitting photons and I want to know, my eye is here, right? I want to know how much radiance comes into my eye, that is Lo. I have to take all those into account, integrate at this point. Now, that's just in theory. What happens is photons are not just coming from the lights. They're also bouncing off the wall and then coming here and then bouncing to my eye. So then I have to model the bounce off the wall, right? So you have so many of these bounces that you need to model before you get Lo, right? And what this means is this integral needs to be recursively applied. One bounce, integral. Second bounce, integral. Third bounce. So by the time you get to the pixel here, you have this high dimensional integral, which is over each of those individual phases. That's one way to look at it. And you have these kind of high dimensional integrals. So not only do we, that's where the dimensionality comes from, right? We've been talking about dimensionality. First of all, there's the dimensionality because h squared, which is the hemisphere, is not a one-dimensional domain. But then you also have this, now it's piling on. So if I have n bounces, let's not call it n because n is the number of samples. If I have k bounces, now I'm going to have a k-dimensional space. And as you know, light may bounce infinite number of times. So in theory, this is an infinite dimensional integral, right? Now suddenly we see, imagine if we had used one of those polynomial formulas, right? It'd be hopeless. We're at 1 n to the infinity. 1 over. But there are ways to solve this, and one of them is through this very elegant formula. This was actually my PhD supervisor who sort of coined this in '94, and it is widely used because it's a very elegant formulation for this transport process. So what he said in there was, let's forget about all these complex-looking things. Let's see what is the simplest equation that can characterize this process. And he came up with this process, this equation, and you can see there's L. There's L on both sides, right? So there's L here, and there is L here. Why is that? Because clearly it's a recursive process. Something needs to be done recursively. So obviously your formula should have some recursion. And he said there's some integral operator here that accounts for the integration. Now, if you look at this is not very different from what we said before. This is the outgoing radiance. This is the incoming radiance. Both are radiance in different directions. This is the integral operator. So we wrote down at each step, we have Lo equals integral of Li something, right? This, let's assume, is some operator which takes care of that. This is the emitter which tells you where the photons are coming from. It's some constant. And then he explained how you can simplify this. And it turns out in mathematics, this is a very standard equation. If you have an integral operator and you have this form, so it turns out you can simplify. I won't show you all the steps, but you can write L in terms of some sequences of bounces times E. So the crucial thing here is now, on the right side, there's no L. right? There is only E, which is the emission. We know that. We know where the photons are coming from. If you're thinking in terms of vehicles, you know where the source of the vehicles are. If you know that, then all of our estimates don't depend on recursive evaluations. However, the cost we've paid for this, or the price we paid for this, is we've introduced an infinite series. And actually, this makes a lot of sense because we saw already that every time you bounce, there's another integral dimension. So it makes sense that you have an infinite number of these k. So k squared means double integral, k cubed means triple integral, and so on. Because k is an integral operator, right? And what this means, allocated your series here, then you will get only one bounce. You get one integral, one bounce on my notebook. If I go to k squared, then it goes to the wall, and then the notebook can be. If I go to k cubed, one more, and so on. In practice, in theory, you have to add up all of these to know exactly how much radiance comes. For a computer graphics application, I may say, okay, let's just ignore everything here, because the amount of light will drop, right? Every bounce, there's going to be much. So there's two things happening here. I think we should leave it at this before lunch. It's 12:30. Do you have any questions before we leave, so that you can remember that? No. Was the jump too much? Do you want me to break it down after lunch? So the light source, here you mean, here. So this, you can either actually photograph a light, which is what people do in the movies now. Like as I said, you can get an environment map where you go and measure. Or you can model this as well. If you can model the geometry and you can model the light, that's, for example, these lights would be very easy to model, right? It's just a square hole, square diffused plate. And you assume that it's emitting photons in all directions. In practice, it's fairly diffuse, so it will be reasonably uniform distribution. But in theory, it could be peak. So if you have a spotlight, so this projector is emitting photons in a very directional way, right? And it's limited to these set of directions, whereas the light source on top is just emitting diffuse out into all directions. So if you can model it easily, then you might as well use a model. If you can measure it and then build a model over it, you could do that. That's what people do in the movies, and that's what actually adds a lot of realism. There was a big jump in visual realism when they went from modeled light sources to captured light sources. Similarly for materials, people were modeling materials and giving it certain distributions in theory, but when they actually measured when they actually measured how certain materials reflect photons, which people in material science have been doing for many years. So when they used those models and they actually measured real materials, suddenly the visual realism went up by a large amount. People were suddenly unable to distinguish what was real, right? And so I would say that the big factor today is, can you measure and model rather than theoretically come up with, oh, let's assume a Gaussian light source. If you assume a Gaussian light source, suddenly all your integration may become easier. You may be able to prove things, but it may not look real. Whereas if you measure the light source, then all the modeling and analysis becomes really hard because you have to fit a model and then you have to try to push it through all these stuff. But it looks real. And I think this sort of problem exists in many fields. It's just computer graphics is an example. In whatever field you're in, there will be a trade-off between using a simple model and using, costly computation, but real data. And I think as we get more and more data, that we're kind of merging into this hybrid where you make measurements and then try to see if you can push it through your mathematics by modeling it using something reasonable. So if I can say mixture of Gaussians, which was probably about 15, 20 years ago, mixture of Gaussians were really big because people would take this function and say, oh, let's model it not by a Gaussian, which was what people were doing 40 years ago. We'll model it with a mixture of Gaussians. Suddenly you could do many more things. Then about 10 years ago, there was Gaussian processes. And people said, oh, let's assume this whole space can be modeled with a stochastic method, like regression technique, like Gaussian processes. Then you had nice things you could do with it. And it was still analytically somewhat malleable. But now, I think it's getting harder and harder to do that because the data is starting to show all these variations that may not easily fit these things. So now the popular trend is to sort of take a step away from our course. The popular trend is to throw everything at a neural network, right? Like you can have a really large, you've probably all heard of, CNNs and Google and all these guys throwing data onto large networks, learning stuff, right? And they are able to learn these kind of things without worrying about, but the cost is obviously data. And the second thing is, with those methods, it's hard to sort of interpret. It's getting easier now, people are starting to understand it, but very few people in the world actually understand, what will happen if something is changed in there, or what should you do to get certain behavior. Whereas with this old school approach, there are formulae and things. But again, with the old school approach, there are disadvantages, like I showed, right? You may have a lot of bounds proved about a method. Suddenly you throw out a certain amount of data, certain distribution or certain type of data, and they're all over the place. You can't tell which slope is better, which pixel is better for which method, and so on. So there's a lot of things to reconcile. And depending on the application, this type of data is usually hard. And remember, all of this stuff that I'm talking about is not adaptive, right? We're still dealing with the simple idea of randomly throwing things without knowing which area to sample better, right? So none of this is adaptive. In practice, what we want is we want adaptive sampling. If we know that the light source is here and the camera is here, we don't want to be sending photons in this direction, right? And we want to be trying to focus our computational effort to photons that are going in here. So maybe you don't even want to throw photons from here if you knew that they're not going into the camera. But how do you know this? So a lot of work is put into achieving these kinds of tricks. And that may require engineering. So you have the scientific aspect, which is a lot of the things we've talked about, maybe the proofs and understanding all these different sampling strategies. And then there's the engineering aspect, which tells you, for this particular application, how do I optimize my calculation, knowing things about the domain, knowing that certain photons will not end up at the camera. How do I redesign this process? So this is where computer graphics split from neutron transport. So for World War II, when they did simulations for neutron transport, a lot of the Monte Carlo methods were born then. They knew they were in a reactor, maybe spherical reactor. They knew there was nothing else in the reactor. So you can imagine, if you know that your photon is never going to bounce on any object in this room other than the walls, you can obviously make a lot of simplification. If you know that your boundary conditions are going to be this sphere with certain neutron reflectance behavior, then you can bake all that and you can simplify your calculation. The problem here in computer graphics was early methods could make these assumptions. Now we can't. We just might get any model, any light source, anywhere. And the question is, do those models still work? They do work to a large extent, but they're very expensive, so you need to trim them down. And for that, you need to diverge from whatever this neutron transport invented. And we need to say, in our case, we have all these other things, and we need to redesign. So I think this is the exciting space for a heterogeneous group like this, who each of you may have different applications. I think this is the key. Is anytime I say anything about computer graphics, think of things in your space. In fact, if you have a doubt in your space, please ask me. I may not know your domain at all, but that will be interesting, because I think the more we think about these things or how they extend to other domains, the more constraints we will have to improve things, right? So if you think in your domain, there may be something relevant here, but the constraint is very different. Don't hesitate to put your arm up and say, oh no, in our domain, we can't make this assumption because of something else, right? And that's what I'm hoping to get from this course as well. And for you as well, if I just keep telling about computer graphics, you may think, I'm never going to use this in my life. Why am I listening to this? But that's what I know. I know how to do this very well in this area, but I'm hoping it can generalize. So that's part of the motivation for me as well. Right? Okay, I think that's already a bit late for lunch. I hope you are okay with that. I think the plan is to resume at 2 o'clock. If you want the extra 10 minutes, then that's fine, because we're breaking late. But yeah, so otherwise, let's meet at 2. Right? And yeah, so if you want to discuss any of this stuff over lunch, tea break, whatever, don't hesitate. And also, I am put up here at CVS. So that's a guest house within on campus. So if you want to ask me anything, feel free to drop. Oh yeah, does everyone have my email? No. Okay, I will give you my email. I think what I will do is maybe, yeah, I will share a Google document. I'll give you my email, and I will share a Google document. And it'll be nice if you can all put your emails there. Because then if I want to send a message out to everyone, I can simply use that. And also what I'm going to do is I'm going to put all this stuff, maybe tonight, whatever you've seen already, I'll put it into a Google Drive, and I'll give you all access to it. So if you have a Gmail account, preferably put that, because then it'll be easy to access Google, but it's not necessary. I think you can still access things. So you don't need to send me anything now, but I'll give you my email. It is just my first name, so put it here. So I'll give you, so it is Kartic at Gmail. Shouldn't be hard to remember. The only thing is the spelling. It's TIC. That's how I spell my name. So if you remember my name, you should be able to remember my email address fairly easily. So if you want to drop in an email about any question, anything, feel free. What I'm going to do is I'll set up a Google document. You don't need to send me your email for now. And I will, oh yeah, how will I send you? What I can do is, we don't have a website, right? Hey. Yeah, okay, that would be complicated. So perhaps I will pass a sheet and you can just write it. Maybe that's the easiest. Yeah, please write it legibly. I don't want to be spamming other people with information about this course. So once you have written your name, feel free to go for lunch. Another thing I didn't say is if there are parts of obviously the group is a bit mixed. Some of you are computer graphics experience, some of you are not. And obviously we have other people here who may know much of this stuff. So if it's something you already know, feel free to carry on with any other work you have. If you have a laptop, I'm not going to be offended. If you have to leave for a meeting or if you're bored of class and you have to leave, that's also fine. It's totally meant to be interactive. If you want to say anything, raise your arm. There's no point holding you here if you're bored. If you want to sleep, put your head down and sleep. There's absolutely no problems with that, right? I think we may have to cover certain topics that people know. And I'll try to make it in a way that people who don't know will learn something, and people who know it might realize something else about it. But if not, then I think we have to accept that. Okay, so I'll see you guys at 2. And whoever has the last sheet, if you could leave it here. Oh, I just wait. Yeah. So if you've written your name, you can go for lunch. Yeah, feel free to ask about lunch as well. So originally the plan was we would have labs in the afternoon where you do practical stuff. And in my original proposal, I had only proposed 2 labs. But then the government reviewers came back saying, oh, there are only 2 labs, make it 5 labs. So I made it 5 labs, and I've designed material for 5 labs, but I feel it may be more useful, depending on looking at these things, to cover some of the basics. For example, probability theory basics, or Fourier transform basics. So, because suddenly we're going to be jumping into, so even things like this, I was not very comfortable showing them. This one. Yeah, so when I showed you this, this recursive integral and stuff, I'm not sure. If you've looked at integral equations, it's very basic. But if you've never seen integral equations, this is not trivial, right? I mean, explaining why k is an integral operator, why is it a linear equation, all these things are not obvious from this. So I can maybe cover some basics there. Again, there's something that may not be important, right? Like you may not care about details here. So it's going to be a bit tricky to be in between. So what I'll try is this style, I think, of doing some things, in more low level, and then this style where for complicated things, like if I have to teach you PDEs and integral equations, we need more than 5 days, right? I mean, so I don't hope to also cover all these things. So how many of you are comfortable with like PDEs or calculus. So basic calculus. Okay, so then I think, but PD is not everyone's comfortable, right? Or integrals, integration is no. Okay. So then maybe what I'll do in the afternoon today is I will have a primer maybe with some probability. If you have any questions, that would be the ideal way, right? Like, so I'll start with some things, and if you have any questions, like things you would have heard of. So one of the problems with a lot of these things is often people use terminology. And I think especially in industry, that's a big problem, right? Like people will say things and everyone knows them. And so you're familiar with the idea of an expectation, but maybe you've never actually written down what an expectation is, right? So if I say expectation every time, I'm thinking in terms of what I know as expectation, and you are thinking in terms of what, so there'll be a big mismatch on any of these things. So I think rather than, that's why even all of this stuff, I prefer to teach bottom up, right? So if I say, okay, today's lecture is on Monte Carlo, already all of you who know something about Monte Carlo will be on a different track. Whereas if I explain this and say, oh, this is called Monte Carlo, at least we're on the same page, right? So I'm going to try to do that. But if you have any buzzwords or any of these terminologies, even things that I use, if you're not familiar, you should just raise your hand and tell me, and we can make a list of those, and I'll try to sort them and present what each of them means. Okay, so even over lunch, if you feel you have a list of buzzwords, or maybe I'll keep one sheet out here, right? So I'll keep one sheet out here, and I will write, just title it buzzwords, right? So if there's anything or terminology, I can call it. So anytime you walk in or out, feel free to just write down what that term is, and then we'll, if I know it, I'll explain it. If I don't know it, we'll Google for it and see what the answer is. Right? Is that good? Yeah, so important thing is please speak and talk a lot, because 5 days of me just talking.